Not sure if everyone's here, so we'll just get started. I got to leave it a little bit early, so I want to get my introduction in, and we'll get to the regular session that we have. The one thing I want to point out here that you'll notice we have plenty of breaks, so hopefully it won't be so painful. Seriously, the only way that we're going to make this interesting, if you have any questions, we're really presenting an overview, not really a training session, so we're not going to get into formulas or approaches. So anyway, we're going to make it interesting. If you have any questions at any time, please interrupt any of the speakers, and they'll be happy to answer your questions. All the presenters are top-notch guys. So getting started. Oops. Of course, this is the Civil Structural Architectural training session, and as I mentioned, it's not really a training program. It's more or less an interview of what my department does. My name is Lou Garcia, and of course, I'm the manager. Sometimes I'm the manager, I'm not quite sure. Sometimes I'm the chief engineer, lead engineer, depending on our engineering manager, what his mood is today. But again, officially my title is Manager of Civil Structural Architectural Engineering. And I mentioned, I think you have in your handouts here the class schedule. I'll have a brief introduction. We'll have a presentation on C-lift modules, plants and refinery, and Manny Dizon will prepare his presentation on civil. And looks like one. Yeah, before I don't want to bypass the safety moment, but before we start the safety moment here, I just want to mention the organization of my department in case you have any questions in the future. We always put our civil group last, so I'll start with Manny Dizon. Manny Dizon is my chief or lead engineer as far as civil engineering. So if you have any questions, please refer to him. In structural engineering, I've got two representatives, basically Amin Khanna. I consider our specialist as far as Arctic design modules. He's got 30 years of experience, plus or minus. Very experienced. Got a PhD from Berkeley in structural engineering, and he's had the opportunity that some of us would like to follow through all facets of the design. He's designed the modules. He's led projects as a lead engineer. He's gone to the fabrication, the shops, to see the steel being fabricated in various locations. He's gone to the assembly sites to see the modules put together, and he's gone up to in both locations, up to the North Slope in Alaska, of course, to see them installed. And he had an opportunity, I believe, to go to Sakhalin Island there on that project. For petrochem refinery type work, Dan Samani. Dan Samani is basically my peer. We've been together basically for plus 30 years. So again, he and I have the most experience. So if you have any questions as far as refinery, petrochem type applications, don't hesitate to contact Dan. The other representative that's not here is our lead architect, Tom Black. He's not going to make a presentation, but again, if you have any questions as far as architect issues, please don't hesitate to contact Tom Black. So with that, we'll go into our safety moment. It's a safety moment, and it's a commercial or a plug for our safety-based safety training. I know we have I see most of you are new, so as you know, we had two modules previously. Now we currently have an additional third module. And I know most of us don't like to spend the time with going through the modules, but really there's some helpful tips there, especially for I think most of you. And I know that in our group we go to the client job sites or the locations, the vendor shops. So this is basically, and then if you pass that back, if you take a look at this, again, this is a plug for our safety training. Again, what I want to emphasize, even though with our clients. There's a lot of emphasis on safety, that we still have accidents. There's two incidents here. One is that as the photos are going to be coming around, there was two fatalities in the recently. One was at a steel fabrication shop in some shop in Canada. This is for the structural guys. We commonly visit the fab shop, so this is an occurrence for us. And as you see, when the photograph comes around, they were setting up a rigging to weld a tubular beam elevated about 2 meters, so it's about 6 feet, 8 feet above grade. They had temporarily tack welded this long tubular beam. I think it weighed a ton, 2,000 pounds, temporarily. someone miscalculated the welding, so when they started doing some work, the beam, the scaffolding collapsed, and unfortunately the worker there was killed. So it's an unfortunate thing. For us, when we go to the fab shops, take precautions. The other issue, again, I don't want to, obviously the owner's name is there at the bottom of the release. There was another fatality at a refinery at Texas City. There's a lot of emphasis, I know personally, and you probably have had the experience also, when you go to the refineries, there's a lot of emphasis on safety. Even so, there was another recent fatality. They were doing some maintenance, startup work for electrical guys. When they were starting to do some troubleshooting or startup, unfortunately, one of the workers was electrocuted. So again, the issue is, again, when you go to the job sites, when you visit our clients' facilities, when you're working around the office, please take precautions. And again, there's some tips there in our computer-based safety training. So please, take the opportunity to go through those, and don't view them as a chore, because they are some helpful tips there. So with that, I'll briefly be touching on the topics that you see here: the purpose of a structure, interdisciplinary relations, structural materials, codes, structural loading, load paths, structural analysis, construction, foundations. You can see that my slide here was put together by the structural group. There's no mention of Manny's activities, but he'll be giving that. And I forgot one additional person that we have here, and I want to thank him for preparing the majority of the work here. And if you have any technical questions, please ask him. That's Ahmed Hader. So if you have any difficult or technical questions, please ask Ahmed. So with that, we get into, again, an overview of basically, in this case, a structural, the purpose of our structures. We basically provide structures to support the process equipment. You've had presentations before, and of course the process people know that there's basically 4 or 5 basic elements that we always see: vertical vessels, reactors, vertical vessels, the horizontal vessels, pumps and generators, and a lot of piping. So for our group, the purpose of a structure is to support piping. There's always pipe racks, whether it's a single T-support for a single line, or you see a multiple level pipe rack here, probably an interconnecting pipe rack, 2 or 3 levels. We always provide support structures for pipe racks. We provide, in some cases, reactors. We provide either concrete or steel support structures and foundations for reactors. Commonly, the reactors are elevated above grade for maintenance purposes, so maybe 10 or 15 feet. So we provide either a steel or a concrete structure to support the reactor, and of course a foundation. For the other elements, we provide, of course, for foundations for vertical vessels, horizontal vessels, exchangers, compressors. Compressors for us, in some cases, are interested because we have to do, in some cases, some dynamic analysis, which for some of us is a deficiency, including myself. It's a really interesting design. We have to calculate the natural frequencies, make sure that there's not resonance between the frequencies of the structure, foundation system, with the operating speed of the machine, and also keep the vibration limits due to the unbalanced forces within tolerable limits. And of course, when we get down to some of our Arctic applications or skids, the truckable modules are to contain small self-contained units, for example, a pump module. Of course, Amin Kanal will get into more detail here, but again, purpose of a truckable module is to provide a small self-contained unit, and then we get into what we consider the interesting part of our work, the sea lift modules, where there is to more or less provide almost a complete unit, and I'm sure most of you have been exposed to the sea lift modules. Interdisciplinary relations. When I was making my dry run, I made the comment that some may find funny or not, but we like to feel in structural that we're the premier group. But the truth of the matter is we're a support group, as much as we hate to admit it. And by that I mean is that no matter how qualified or what experience we have, without the support of the other disciplines, we can't do anything. If we have any piping designers here, without the piping layout, we can't do any piping. We can't do any pipe racks or layout. Without the equipment, we can't do anything. So we're really a support. And as you can see here again, as much as we hate to admit it, piping is our main client, and of course we have the interface. This slide here that I'm pointing out really is my favorite slide here in my presentation, and it shows how we interface or react, and more important, how we're fully at the mercy of the other disciplines. Of course, we interface or react as we all do with our client. The client provides us our scope, our budgets, etc. And when there's a conflict or a resolution as far as his design criteria or what he wants done, of course, we interface with our client. And as I mentioned, our main interface with piping design, process equipment, vessels, horizontal vessels, we need that information. We always, as much as we don't like to do, interface with the project engineer. Of course, architectural is part of our group here. We don't really have much interface with piping material normally. And of course, and also with mechanical process, we don't have much interface. But basically, again, piping, piping stress, the equipment, and of course, we all, as most of us do, have to procure some material. So we're involved with purchasing.
So you missed one discipline there.
What's that, civil?
Yeah.
No, you're part of the group. You're part of the group, Manny.
Okay. I'm just kidding.
Structural materials. We basically deal with two materials primarily, and some other materials. But basically, we always use steel. And steel here is for superstructures. Where superstructures, as you've seen in the previous slide, can be for pipe racks. They can be for support structures like the reactor vessel that I mentioned, or they can be like for the sea lift modules. For the superstructure is all the steel above the base, what we call the base. For foundation work, we use, of course, reinforced concrete, although for some structures and even for some pipe racks, we have used a reinforced concrete. The choice is really if a pipe rack, for example, needs to be fireproofed. In some cases, it's found to be more cost-effective to use reinforced concrete columns and beams as opposed to using a steel and then fireproofing it, etc. So, but again, the majority of use for our foundation, for reinforced concrete, is for foundation usage. Steel embedded in concrete, again, this would be primarily for anchor bolts to anchor down the vertical vessel's equipment. Fireproofing for steel, and one item that's not here, and we don't do much in that, and that's for small buildings like a substation, for example. We use masonry block. Masonry block for us is kind of an interesting design also. Structural codes. For us, this is really the interesting part, and I've gone through some of the universities for interviews, and it's really puzzling for me. The reason I say it's interesting is the codes that we have are constantly evolving, and I'll get to them in a second. The steel code, concrete not so much anymore, but the loads here, whether it's ASC or the IBC, but these are constantly evolving. I've been in design for 30 years, and just when you think you've got more or less of the major items covered, there's a new approach that you have to do some more studying. The reason I say that I've been a little bit disappointed when I visit the universities that I've talked to some of the students that we try to recruit, and the comment is, well, I've already gone through the design process and I want to go into construction management because I don't think there's not much left to learn as far as the structural design, which to me I find a little bit naive. But anyhow, for as I mentioned, for steel, our main code is the AISC, American Institute of Steel Construction. It's currently in the 13th edition. When I started design work quite a few years back, we used to refer to the black book. It was about an inch thick. Now it's about 2 inches thick, and there's an accompanying CD. So there's been quite a few changes. We're currently going through a real interesting evolution. The senior experienced fellows like myself have been used to using the allowable stress design, where basically we compare the stress in a particular member with the yield strength divided by a factor of safety, which gives us a so-called allowable stress, as opposed to the like concrete to ultimate or strength design or a factor design that we're currently using. There we compare the demand of a structure with some load factors for dead load, live load, with the yield or the capacity of the member. So it's a different approach. Again, it's quite a change for us that have been using the allowable stress design. But again, I assume that probably, as in concrete, the The next edition or the following revision will be just one approach, which again will be a strength design approach. Concrete, when I first started designing 30 years ago, we made the transition from allowable stress design to ultimate strength design. So this is pretty much common now. And for our loading, one code that's not here that you may have heard of, the Uniform Building Code, which is now evolved into the International Building Code. The attempt there is that previously nationwide there was 3 or 4 major codes. In the West Coast we used the Uniform Building Code. In the Southwest, southern areas they had the Southern Building Code. New York, I'm not quite sure what that code was called, but there was 3 or 4 major building codes, and now the idea is to have a uniform or international building code, international basically for the United States. So what you don't see here is the International Building Code. International Building Code really refers back currently now to the ASC 7. So in the future, the International Building Code will by default say that for wind analysis or for seismic design, see section such and such of the ASC 7. So basically it'll default to the ASC 7. And the fourth item that we see, I believe in the other disciplines also, about 10 years ago, our major clients, our competitors formed the PIP. The effort there was to consolidate the various design approaches, construction specs from all the clients like the BPs, the Chevrons of our competitors, the Fluors and the Bechtels, and to have a uniform approach as far as design practices, construction specs, with the hope of having a more uniform, a more quality product, and of course, ultimately to have a more efficient, cost-effective design. So there's a lot of information here, and I believe all the other disciplines, electrical, instrumentation, the vessels also have a similar session in the PIP. Structural loading, we're getting short of time here, so I won't spend too much time on here, but just basically the loads that we have are, of course, dead loads, which are the permanent fixtures. For example, the structural framework of this building here, obviously, is a dead load. We have live loads. In this case here, all you sitting here, for example, would be considered a live load. Any in the refinery type applications? Sorry? We had some dead loads somewhere? Did I miss? Live loads in the refinery would be the liquids, the contents of a vessel, for example, would be live loads. Of course, temperature loads, those of you in heat transfer know the temperature loads that we have as far as expansion. Wind loads I'll talk to briefly in a bit. I'll touch a little bit more briefly. Seismic, and of course test loads, lifting, sea transportation loads. I see Mike McKenna is here. I think he's our expert as far as transportation loads. We have very high barge acceleration forces, which result in significant loads. And of course, also Mike McKenna's specialty, transportation, rubber-tired vehicles, so-called RTVs, which present another set of loads for us. These two topics here have evolved over the years. Our current, I think most of us that are in my group here worked for a previous manager, Sam Lawrence. So he would be very happy presently, because the seismic loads now have evolved where it's very difficult, and in Sam's comment, you more or less have to have a PhD to do seismic design. So really he'd be happy. But this has seen quite an evolution. Now, I think most of you are familiar with the seismic zones that we used to use in the Uniform Building Code. And as you may or may not know, the seismic zones are gone. They no longer exist. And what we have now are site-specific accelerations, the short-term and long-term, based on, of course, location. So it's a very interesting, but it's quite tedious. The same thing with the wind loads. The previous versions of the UBC, it was very easy to calculate the wind loads, and now they've evolved into what used to be the ANSI 58, now ASC 7, where the wind acting on a structure or building is divided really better in how it affects a structure or building. So interesting, the total wind or the shear from previous codes and the new approach, the magnitude has not changed. It's just that the distribution on the structure or building has changed significantly, and also it's a little bit more difficult to calculate because currently with the wind loads, there's 3 or 4 different approaches. We have the simplified approach. I believe it's called low rise, a regular, and then for a flex I forget the terminology, but the first term. So load combinations here. Again, I'll just touch on this. Basically, the load combinations is based on the assumption that you're not going to have the probability. You're not going to have, for example, maximum wind with seismic. So again, these are load combinations that we get from ASC 7 or from the International Building Code. And again, it's based on the principle that you will not see the maximum different loads simultaneously. So usually we have dead and live, for example. We have dead and live and wind, and dead and live and seismic, but never wind and seismic at the same time. Loading path, if we have any electrical engineers here, it's similar. Forget my ignorance here, I guess we go from high potential to low potential. The current flows, in our case, we have similar, what we consider a shear flow. So the shear flow here would be that there's an applied load here. Shear obviously flows through the beam, flows through the connection, through the column, and ultimately down into the foundation. And so, again, the principles here, principles are listed here. The strongest member takes the strongest load. The foundations have to be adequate to take the loads. Connections have to be able to transfer the loads. Foundations, of course, are adequate. And what is very important in our type of designs is the deflection. Analysis design. I won't go through the bullets here, but I'd just like to mention that the major change that I've seen in my career has been the software programs that we have now. We have a handful of programs that we use in structural, and Manny will probably present the ones that he uses in civil. STAD-Pro is what we use in our office, but there's also a RISA, which our competitors Fluor use, GT Strudel, SAP 2000, and a RAM that's used primarily for buildings such as this building here. This really has a lot of, has really allowed us to be a lot more efficient. The main problem that we have was when I started doing design work, we used to do moment distribution, and changes were not quite as damaging at that time because we couldn't react enough to do our design. So when there was a change, we were halfway through our design, so it didn't make any difference. But now with the software tools that we have, it's very, very quick and efficient. So when there's a change, it really causes us a lot of problems because there's a lot of changes. Construction, I'll just touch, I'll leave this action basically for Amin in his presentation, just a couple of comments here. And the main thing here, I think Dan Samani will have a better presentation here, types of foundation. We have a single or spread footing, we have tied footings, which we have two spread footings tied together with a grade beam. We have a combined footing, which would be rectangular. I can see it's almost time for me to leave because I messed up the screen here. Yeah, and then of course we have variations on pile foundations, whether they be a driven, cord, or caissons. So with that, I'll turn over the presentation to Amin. And again, we have an overview. The only way we're going to make this interesting, if you have any questions, whatsoever, why you do this, or what, if you're interested in the formula, please ask any of the presenters, and I'm sure they'll be happy to answer your questions. So thank you for your time and attention. Amin? Oh, yes, sir.
Yeah, I have to break up your presentation.
The good news is at the end of my presentation, we have a break.
Here, I mean, save your jokes.
Okay. My voice is loud enough. Okay. Okay, I'll be presenting the C-Lift module design. And my name is Amin Kanan, and I'm a senior supervising engineer. And I have been involved for the last 3 years, mostly in modules. This is the outline of the presentation. We are going to show some module pictures and then an introduction, then input from other disciplines. It's always important to stress on the fact that structural, we interact with all the disciplines. Actually, in petrochemical, all the disciplines are related. and they all depend on each other. Then I'll have some more pictures of modules during construction. Then we go through the components of modules, and I'll briefly describe module fabrication and transportation, and then conclusion. So those are module pictures. This gives you an idea what a module is and the proportions of a module. This is another module also. This is a 5,600-ton module. This is probably the biggest designed for onshore installations. And we designed this for GHX2. That was about 10 to 12 years ago. After that, we were doing, this is one module that we did in Sakhalin Island, not for the North Slope, but a similar environment. It's also cold weather. And this is a smaller module, and I'll explain why we have all this extra steel, that is not part of the module, because basically the module is only this. But we have to have some extra steel. What is the purpose of modularization, really? Why do we go for modules? We have two options. Either we can send all the steel and send all the equipment and all the vessels, piping, everything to the North Slope, and they will put it together into a module like this. And that's very difficult because in the North Slope, especially, like also in very hot weather, let's say, we can work, the frame of work is on the window is only maybe 6 months. All the rest, really, the people cannot work. They can work maybe half an hour, and then they have to go warm themselves inside. I have been in the North Slope in December. It's impossible, to go out for inspection or to check if the guy is, whoever is working there, most of the time he spends his time inside. So it's very tedious, and also you cannot get the specialized people to work on these modules. You cannot send them to the North Slope. Very difficult also. It costs more, economy, and speed. These modules, for instance, when they are built in the lower 48, in warm weather like Louisiana or Korea, right now before they use Japan and now Thailand maybe, they are very pleasant weather and they can go very fast. They can build them maybe 6 to 8 months, put them together in six months. It would take maybe several years to do it if it was in the North Slope. Different sizes of module vary. We have modules like for substructure. This is also a module. What is a module? Basically anything could be a sub-assembly. We have from sub-assembly to offshore modules. So platforms, stairs can be assembled into units. That's an assembly. You can have trackable, liftable skids up to 100 tons. Those are that you can lift with a crane and then place them on location. You have onshore sea lift module, which are the sea lift when we use the sieve to transport them. Those will be between 1,500 to the maximum that we did is 5,600. We have done at Worley Parsons preliminary design for modules of up to 10,000 tons, and Mike was involved, and Klaus was. He will give you a presentation about cold weather. He was involved as a piper and put together modules of 10,000 tons, but we never built them. They were just. Maybe we will do that if the gas project goes on. The gas project is a huge project that always we are waiting for approval or to kick in. The exploration of gas, exploitation of gas from the North Slope. There's tremendous quantities, but so far those projects have not been implemented. They are exploiting the gas in Qatar right now, and they do have huge installations. One of the biggest installations, but so far we have not been involved with this project. To give you an idea, offshore modules can be bigger than onshore modules, and they can reach up to 15,000 tons. And offshore modules are maybe sometimes they float them, on the sea because they are very big. I want to touch a little bit on what we need the input from other disciplines to be able to build a module. Basically, the layout of a module is provided by piping, because based on all discipline requirements, they take the information from vessel, mechanical, electrical, instrumentation, operational spaces. Operation is very important also. Lay down areas, OSHA regulations, all this, they take them, they put them together, and they are the architect of a module. So for instance, this module is decided to be very high, because there are some vessels inside, and the operation is such that they need to be on top of each other. Now, the module is dictated, therefore, by piping, and the minimum height above grade